topic of this week is about sublinear algorithm. Okay, like right now, we have big data, right? And the data is so huge that you don't even want to spend your resource linear in the size of the data. You want to spend sublinear, like a resource compared to the data. Today is going to be sublinear space, which is like a topic of streaming algorithms. Next class, sublinear time, and you know about it. Okay? But today, streaming. Okay? So the motivation is like this thing of router, and this example scenario is like for example, router need to process so many IP addresses, right? But if there isn't some attacker that kind of flood the traffic, maybe if you want the router to maybe detect that, right? Or you can think you have website and there are many visitors, but you want to kind of count the unique visitor. If the same guy visit many times, you don't want to count that twice or double count that, right? So one way to solve this is just to store all of the IP address that you have seen. But that is just impossible, right? That's just the issue is just it takes too much space. So we want to try to develop a algorithmic paradigm that address this. Okay? And this is basically the model of streaming algorithm. The model is this. Think of you have a bounded universe like before, right? And the input is the online sequence of elements E1, E2, E3, E4 up to En. Each of them is a number from 1 up to U. Okay. Think of each element as an IP address, for example. And here I say online because I mean that once element T arrive, then the previous one is erased. It's just kind of you kind of just see the stream of the data going through you. Okay, and you don't know N ahead of time as well. Okay, the number of elements. Okay. And the goal is to solve some problems that's useful, such that when you go through this stream of data, you can solve some problem using the space of polylog of U and N. Okay. So you have a big stream, but you have small local memory. But how can you solve anything? That's the goal. Okay. This is a model that is introduced just 20 years ago, sometime, but it's newer than the previous topics that we have learned, and this is introduced by Alon, Matthias, and Sejidi. They get a Gödel Prize from this, which is one of the highest prize in TCS. And by now it's really active research area. If you look up for streaming algorithms, there are several people working on this. Many people actually, yeah. And let's see how do we solve this thing. At least, let's look at some toy problem. Suppose that I want to compute the sum of this number. For each element, I want to compute the sum. Yeah. Do you see how can we do this in the model? Maxim?
Just keep on running sum.
Yeah, just keep sum one counter variable. When E1 arrive, add that to counter. E2 arrive, add that to counter, and so on. Just directly compute the sum, right? And you know that the size of this number is going to be at most U times N. That's the value of the number. But this number, it means that this number takes just log of N times U space, bits. So that's enough for your space. Make sense? Okay. Now let's look at more interesting case. Suppose that I promise you that in this string, that's gonna be like exactly u minus 1 elements, and all of them are distinct elements. Okay. And by the end of the stream, you should find the missing one. Any ideas how can you solve this? Yeah.
Is it specified what the distinct elements are except for the missing one, or
So
no?
So like, it's like if this is like if u is like 5, then the string might be like 4, 1, 5, 3, and in this case you need to return 2.
So then, well, if you know what u is, then you know what the sum of all the elements would be, right? It's just like n times n minus 1 over 2, I think. Or u times u minus 1 over 2, and then you just subtract everything as it comes in, and you find what the
Exactly.
that wasn't given was.
Very good. Yeah. So here you don't need to really like remember everything that come to your stream. You just compute what Scott just said, pre-compute the sum of everything from 1 up to u, and then subtract by all like the sum of all the elements that you have seen. So that's gonna be exactly the missing one. Okay. Okay, so this is a kind of easy example. Now the real problem that we can look at today is distinct elements, which is the problem where when the website want to count the number of unique visitor, for example. That's the problem, and the formal description is here. Like you have the stream of length n from the universe u, and yeah, you want to output the number of distinct elements in the stream, and I denote it by de, distinct element. Okay. And the example here is, yeah, if the stream is like this, then you have 1, 2, 5, 4. So the distinct element is 4 in this case. Okay. Well, there are like some straightforward solution. One is to just like start a whole universe, which is like you have the bitmap for everything in the universe. Once you've seen something, just say that you have seen that. Well, that takes u bits, but that's big. U is huge. On the other hand, you can start a whole stream. For each of an element, it's like a number of like from of where you at most u. So each number takes at most u bits. There are n numbers, so that's n times u. But yeah, like here you think of u and n as something really huge. You want to spend polylog of u and n. Okay. Now we want better. We want something much better. Now it turns out that we need to sacrifice something. There is this theorem that maybe in the next homework we will guide you try to prove this. That is, it turns out that any exact algorithm, even if randomized, need to take linear space. Also, any deterministic algorithm, even if it's approximate, need to take linear space. So it means that if your goal is ambitious to get polylog space, then your algorithm must be both approximate and randomized. Okay? So I will not prove this right now. This might be in the next homework, and we guide you how to do it. Okay. So now we know that we want our algorithm need to be approximate and randomized, and yeah. So today we will show you how to get a good approximation, like 1 plus epsilon for any epsilon, such that the space is poly of log of nu, and poly of 1 over epsilon. And it's going to be like correct with good probability. By the way, the state of the art is really, really good. It's just like 1 over epsilon square plus log u. And it's really non-trivial, but like we will see like a kind of nice algorithm today. Okay. So any question about the goal? All right. Good. So what I'm going to show you is like first I'm going to look at this problem, distinct element, but we're going to look at the threshold version of the problem. What do I mean by threshold version? So I mean this. I'm going to fix this threshold, dE theta, which is like a threshold for the estimate of distinct element, and fix some epsilon, which is like how good approximation I want. Okay. And given this stream, there are two cases. If distinct element is more than my threshold, then I return yes. On the other hand, if the distinct element is less than 1 minus epsilon times the threshold, then I must return no. So there is some gap here. And if the distinct element is between this thing, then I can do. I don't promise anything. Okay. And I want to be correct with good probability. And right now, let's say 90%. Okay. So that's the problem that we're going to focus first. And we will see how to solve the original problem later. Okay. Right now, let's look at this threshold version. Okay. So now, let's talk about the algorithm. It's going to be quite simple. First, we're going to set some parameter t to be some number that I don't tell you yet. It's going to be some number at least 1. And then we sample a random function. Again, this is like, let's say we have an ideal random function that map the universe to this range. Okay. And what I'm going to do, this is an important step, which is I'm going to count the number of distinct elements in a stream that are hashed to 1, which is like look at all the elements in the stream, and basically if it's hashed to 1, then put it into the set, and I count this set, count the size of this set, and put it to x. So note that if there are two elements that like let's say like element 10 hashed to 1 and element 10 appears again, it will not increase x, right? Like I really count the number of distinct elements such that it hashed to 1. Okay. And the last step is just that I'm going to output yes if my counter is at least 1 minus epsilon over 2 times t. Let me tell you about the intuition a bit, right? So you should think like each distinct element as a dot, right? And each dot will hit a target with some probability. Like when it's hashed to 1, it's like it hit a target. Okay. It's gonna hit a target with this t over like dE theta probability because the range is this. Just the inverse of this. And then x basically just count the number of dots that hit the target. And your intuition is just, okay, if there are many distinct elements, many dots, then x should be big. And if there are few number of distinct elements, then x should be small. So at least this makes sense that like we should return yes if x is big. Question about the description of the algorithm, not the analysis. Okay. Okay. So before we go, like we argue why this is correct. Can you tell me how big the space we need to use to implement this algorithm? Yeah, Rob?
I think we need to store all of the distinct elements that are hashed to one, like if there's to check like if we've already included an element in our count.
And how big can that be? It can be big, but you see, like once the number of distinct elements that hashed to this guy, let's say it's more than t. Do we need to store something further? No, because once the counter is more than t, then you're gonna return yes, right? So basically, you just store like a maintain, like so it means that the space is gonna be just t times log u, because you just maintain all the elements hashed to 1, but only do it up to size t. Once it's up to size t, you can just stop and return yes, like you know you're gonna return yes from now. And each of the elements that hash to 1 takes log u bits, because it's a number from u.
So as of right now, are DE tilde and T are both just like, or we haven't talked about how we select them yet?
Like the theta is like a threshold that you, like someone given to you. Let's say it's like 100, and you want to check if this single element is more than 100 or not. So this is given to you. T, I don't tell you yet. We're gonna fix it later. But you see that the space now depends linearly in T. So we want T to be small. Okay. And before we go further, note that we assume that DE is at least T so far, because otherwise, like this can be less than 1. Okay. But this is like if DE is less than T, it's actually easy. Like I claim that if DE is less than like DE tilde is less than T, then you can still take like a T log U bits. Why is that? It's gonna be trivial actually. Like you have some threshold and you just want to spend now like space that is linear in the threshold. Yeah. So
like if DE is less than T, then that means that, or if it's less than or equal to, that means that the size of, you're either hashing to like 1 or I guess less than 1 elements. So you just like count each distinct element, because everything will hash to the same value. So it's just, just like DE log U. Right?
Yeah, like thing like this. Yeah, exactly. Basically, suppose that like if DE is less than T, now it means that I can spend time linear in like DE theta, but it means that, okay, I can just count the number of distinct elements up to this threshold DE theta. Like don't even do anything here, right? Just like store the whole store the whole the whole stream, like look at all the store the whole stream and only store all the distinct element and store it up to this threshold, and you can spend linear, like space linear in DE theta, but DE theta is less than T, so the space is just T basically. Okay. All right. So now we see that the space is T. We want T to be small, but we'll see in our analysis soon that like when we set T to be like just 1, it will not work. and it will work with good probability once t is big enough, and we try to minimize, like make t as small as we can, as long as it's have a good probabilistic guarantee. Okay, so now we just need to analyze this. The algorithm is quite straightforward, but why it's correct is not clear at all right now. Okay, and the analysis will have two steps. Okay, the first step is that at least when we have randomized algorithm, the first thing to do always is almost like just check that in expectation this makes sense. Right. So at least we expect the correct answers. So basically we want to compute the expectation of x and see if that makes sense. That's the goal. Okay, so let's say that I rewrite things a bit. Okay, I write this set E1, E2 up to EDE as all the distinct element, the set of distinct element in the stream. And I define xi to be the indicator that the I distinct element map hash to 1. So x is exactly the sum of xi. Okay. So now we can try to analyze the expectation of x, and this is just gonna be like, you use linearity of expectation, and this is like a sum of this xi, and what is this? What is the expectation of xi? This is a probability that that h of ei map to 1, right? But what is this? The hash function map from u to de tilde over t. Okay. And h is like a random function right now. So what is this? Yeah, John.
1 over the array size, so t over d.
Right.
Tilde.
Right. So this is gonna be this is just the inverse of this guy. So dt over de tilde. Okay. So it means that this whole thing is sum over de elements times t over de tilde. Okay. All right. So I just repeat this. Yeah. We get that like this is de times t times t over de tilde, just because for each distinct element is hash to 1 with this probability. Because we know that h is uniform. H map things uniformly. Okay. So now we have computed this expectation of x. So there are two cases that we need to consider. When de is more than, when like number of distinct element is more than our threshold, it means that expectation of x is at least t. And when distinct element is less than 1 minus epsilon times the threshold, expectation of x is less than this. But we see like in our algorithm we return yes if x is at least this. So our threshold here is basically kind of in between the two cases. Like our threshold is like in between t and 1 minus epsilon t. It's like a 1 minus epsilon half times t. So like just in between. So at least it means that if x is exactly its expectation, then we are correct. Okay. So basically this we are if x is always expectation of x, then we are good. But they might not be exactly equal all the time, right? X is a random variable, so the next goal is then try to say that okay, x should be close to the expectation with good probability. And so then the next step means we want to show that we have concentration of this. X is concentrated to the expectation. Okay. Sorry, expectation is constant. No. Random variable is concentrated. So how to show that X is concentrated? Well, the usual trick is to bound the variance. If the variance is small, it means that you concentrate basically. And once you bound the variance, to show the concentration, it's just to use Chebyshev, which is like this, right? Which says that x will deviate from the expectation by something is bounded by some variance over an amount of deviation square. Okay. So, but this is non-trivial, so I'm gonna do it slowly. We need to compute the variance of x, right? And x is just a sum up to dE of xi. Okay. Now I claim that we can do this. We can put the sum outside. Why is that? Yeah.
Is xi are independent?
Yeah. When xi are independent, you can variance is linear. This is linearity is always the case for expectation, but not for variance. But in our case, it is fine. Okay. And by independence. And now, next, I claim that you can bound the variance by the expectation. And this is because x is a 0, 1. You see, variance of x is this thing, right? Xi square minus xi, everything square. But xi square, when it's 0, 1, it's just the same as xi. So this is xi, and this is something positive, and it's minus, so I can just ignore it. Okay. So at least it means that the variance of x is at most the expectation of x. Okay, this is what I want to show. Yeah.
Couldn't we explicitly calculate it here? Don't we have enough information to? What's the point of bounding it if we know the exact value?
We could calculate it, I think. Let's see. Yeah, we could calculate it, but so far, I think it's simpler. Yeah. And okay, so now let's try to use Chebyshev, right? We want to say that case 1, when DE is more than the threshold. Okay, so we want to bound the probability that we are wrong. Okay, and we're gonna be wrong if what? If x is less than t, right? This is when we say no. But this is, we're supposed to return yes here. But this is this will, if this happens, we say no. So it means that we are wrong. Okay. And so if we try to do this, then what should we do? Try to make it so that it looks like something that we can use Chebyshev. Well, note that in this case, what you have is that expectation of x here is at least t. This is what happened here, right? Okay, so it means that I can just replace this thing by expectation of x. And now I can rearrange it a bit. Of x is less than just rearrange things, right? And now I can make it that to look like something that I can use Chebyshev now, which is just put the absolute value here. Right.
Just talking P. Big sugar P.
Okay, and now I can apply Chebyshev.
Maybe get K.
What I'm gonna get is just gonna be variance of x over this thing square, expectation square. Okay, but variance is less than the expectation at most, so I can cancel this thing with this. Okay, so this is basically gonna be this thing, because t is at least this. So now you see that when t is big enough, then this is going to be small. Yeah, Rob.
This might be kind of a dumb question, but can you just explain how you bounded the variant, the very last step that you did with the math? How does,
Here.
if you're subtracting a positive value, I'm a little bit confused how you can say that that's, now you know that that's greater than the variance. Can you just explain that again?
This from here to here.
Yeah.
Right. So here, this is just from the definition of variance. This is
Right.
And now, the first term is exactly the same.
Yeah.
And so, this whole thing is at most 0, because this is something square. So this expectation square is at least 0. So now I put a minus. So this is at most 0.
Okay. Yeah.
Right. Make sense? Okay. Okay. So now we have that in the first case. The probability that we are wrong is something like 1 over epsilon squared yeah, 1 over something like epsilon square t. So if we set t to be something like, let's say if we set t to be like maybe 10 over 10 over epsilon square, yeah, 40 over epsilon square, then this would be now like 1 over 10. So it means that we are wrong with like 10%. So we are correct with 90% in this case. Right? So you just analyze it and you can see that like just try to set t so that this is small enough that so that like you're good with your objective. So far you follow this?
Just on the last step before you did the less than or equal to 10, can you explain quickly how you get from 1 over epsilon over 2 squared times e of expectation of x is less than or equal to 1 over epsilon over 2 squared times t?
Sorry, from which step to
In the last step,
here?
yeah, that one to the next one.
To here?
Yeah.
Oh, so first of all, this I cancel because variance is at most expectation. So I can just say that, this is at most the expectation. So if this is at most expectation, I cancel the square. And next, t is at least expectation. No, sorry. T is at most expectation. So I divide with something less than before. Okay.
Since t is dependent on the probability that you want and epsilon squared, does that mean that epsilon's arbitrary?
Epsilon is arbitrary, like it's set from the like someone set it, and like epsilon is like an input, yeah, and we want to be like and then once epsilon is set, then your goal is to certify this thing. Like the smaller the epsilon is, the smaller the gap is, yeah. And t is some number that in the algorithm that right now we are free to set, so that we can solve the problem. Right now we see that t is big, then the space is big. So we want t to be small, but we now see that if t is too small, then the correct probability is not great. We need to set t to be big enough so that the failure probability is small. Okay. So this is the case. Everything is good so far. Okay. So if I set t to be this big, something of order 1 over epsilon square, we are correct with 90% in the first case. It turns out that with a similar calculation, really the same, like almost the same, you can make it just follow do some algebraic manipulation. You can again get to this thing that in this case when dE is less than 1 minus epsilon times dE theta, you're gonna output something wrong with this probability. 1 over epsilon over 2 square times t. So if you set t to be this big, in this case too, we're gonna be wrong with probability at most 1/10. Okay. Good so far, yeah?
Sorry, and just to get from the step, like probability x greater than or equal to 1 minus epsilon over 2t to the next one, you just distribute t and then add it, or and then subtract.
Which step, sorry.
So like right at the top, that one to the next one. You just distribute t and then basically subtract it from both sides. Is that?
I distribute, let's see. Let's see. It's just some algebra. 1 second. I minus t here. And let's see. I forget the calculation, but but like it's not true. Yeah, let's keep this for now. Yeah, but it's gonna be okay. Yeah, for sure. Because I did this calculation, but let's verify this later. Yeah, it's some calculation. Yeah. Okay. The point is just the point. The point is not calculation. The point is like the strategy. When you try to approach this, just like try to bound the variance and apply Chebyshev, so that you see that like your random variables doesn't deviate from expectation too much, and you can try to boost the probability that reduce the probability of deviation as much as you can just by setting t to be big. Okay. So now for now you can see that you can set t to be 40 over epsilon square, and it means that your space is something of order 1 over epsilon square times log u, and you are correct with 90%. Good. But you see, we still use random function, and we try to remove that because the space of random function is just linear. We don't want that. And today we're going to use something that is stronger than universal family. It's going to be two-wise independent family. Okay. So if you should recall this. And last time we used some hash function that satisfy small collision property. Today we're going to use this one. And the property that we want is basically all of this is just behavior of random function. One thing is just pairwise independent, which is for any two different elements x and y, and any ij from the range, ij might be the same, then xi mapped to I, x is mapped to I, and y is mapped to j with probability something like 1 over m squared. This is what pairwise independent is. And if your function, if your family satisfy this one, it would satisfy this one and this one. Yeah.
This is just to recap before, but the families that we looked at before didn't satisfy uniformity, correct?
Yeah.
Because if zero input will always map to zero.
Exactly. So the family we looked at before is satisfy this, not this one. Today it's gonna satisfy this one. So both of this. Okay. All right. So this is the family that we want, right? If it's the family of function that map the universe to some range m, and if we said that it's two-wise independent, if basically what we expect the definition, if you sample a function from this family, then it behaves like it satisfies two-wise independent property. Okay, so I'm gonna give you an example of some family that satisfy this, and today I'm gonna prove it to you. Okay. So the family is gonna be. So let me change from small u to small m to big U to big M for my so that this is for convenience of notation, and because I want U here to be the set U is gonna be like a bit string of length U, and M is a set of bit string of length M. So now big U is like of size 2 to the small u, and big M is size 2 to the small m. Okay, so I changed the notation a bit. And I'm going to define here, given matrix A and vector B, H, like the function that is defined by A and B is going to be AX plus B. And we do everything mod 2. Okay. So if you know finite field, we do it over finite field of size 2. Okay. And the picture that you should have in mind is like this. Like X is the vector from like long vector, right? U is, you should think of U as something big compared to M still, right? X is something big, and what we compute is X times A and plus B, and then you get your hash value, which is like a short vector. Okay. And the family is just this. Like just HAB for all possible A and B. All possible matrix here and all possible vector here. It generates some function HAB. Put this function into the family.
Sorry, what's the notation again for the bracket U?
Bracket.
Like bracket 0, 1, and then
Oh.
this one, yeah?
Like this is a set of bit string of size U, of length U. Set of bit string or vector of size, like, okay, maybe this is like, you think of this as a vector of U elements. Like each of this is like 0, 1, and it's like a U entries.
Oh, okay.
And the same here, like 0, 1 vector with dimension n.
Okay.
Make sense so far? Like this is just a matrix. Each element is from 0, 1, and the dimension is like a U, like M times U. B is like a vector of dimension M.
And for any given hash function in that family, A and B are like constant, right?
Yeah.
Okay.
Yeah.
Wait, and A is, it's not just a super long thin vector going with 0, 1s. It's,
Say again?
A isn't just like 2 by M by U. Like it's not just a bunch of 0, 1s. It's actually like balanced.
It's a matrix. It's a matrix.
Yeah.
Yeah, like a matrix that has like M rows and U columns.
Okay. Oh, and each is just 0, 1.
Each of them, each cell is 0, 1.
Okay.
Okay. And like for any A, which is a matrix of size M by U, for each B, which is a vector of size M, it defines a function. Put that function in the family. Okay. And yeah, like what we're gonna do is just like a sample of function from this family. And you see that each function takes space something like mu times m. This is basically the number of bits in A. This is u times m, but actually it's actually small. Because here, like the size of your range and domain actually is like 2 to the u, 2 to the small u. So this is actually like takes space, polylog in the size of the domain and range. Okay, so the space of to represent h actually is actually small, like polylog. Okay. But next thing that is important is to show that this family is two-wise independent. Okay, so I'm going to show that. Okay, so what do we need to show to say that it's two-wise independent? Means that for any x and y, right, from the range, from the domain, that are not the same, this is u, and let's say alpha 2 from the range, we want that, we want to say that like the probability that h of x map to alpha and h of y map to alpha 2, this is something like 1 over this thing, which is the range square. This is what we want to show. Just from the definition. How can we show this thing? Once, if H is sample from the family. Okay. So this event, I claim that this happened only if let's say that, yeah. So H A B map X to this thing and H A B map Y to this. If and only if what? First of all, plus B is alpha 1. Okay? But I claim that it's also true if this is the case. This is equal. Okay. So because actually the second equality that I have is this thing, right? But what I do is just I subtract, this thing is obtained by having this one subtract by this equality. So I get this thing. Okay. Right. So maybe I just said I just said this here. If this happened, then you have all of this thing. Yeah.
Sorry, what is x2?
Oh, sure. Yeah, sorry. I mean y. Yeah, I mean y. Let me say x2, just to that x1 and x2, and this is x2, because I used alpha 1 and alpha 2. Now it makes sense, right? Like I have this thing map x1 to alpha 1, map x2 to alpha 2. So this happened when all of this happened. This is just what it means to map x1 to alpha 1. This is what it means to map x2 to alpha 2. I subtract this equality from this, I get this one. And now, the probability that this thing happened. What is the probability that B equal alpha 1 minus this? So we know that we sample H from the family. So B is just a random vector of size M. Right? B is just like this vector, 0, 1 vector of size M. The probability that B will be like for each bit of B is equal to something, it's gonna be like 1 over 2, because each entry of B is just random. This part is just independent from B, right? So now, for each bit of B equals to each bit of this thing, each of the bit agree with probability 1 over 2. So and we need to this for this to be equal, this event must happen m times. So this is just 1/2 to the m. Okay. What about this event? The event that to look at this event, I'm gonna like divide. Let's say that I define c to be x1 minus x2, right? And note that like x1 is not equal to x2, so there must exist some entry such that ci is 1. Because the x1 and x2 are not the same. Okay. So now, okay. So now I claim that. So now I just write the probability, right? That AZ is equals to minus this. Now I want to analyze the event that this thing happened. Yeah.
Is Z the absolute difference between x1 and x2? Because you could have like a bunch of negative ones.
Right. We are doing mod 2 right now. So like when it's -1, it's just 1. Yeah, mod 2. Yeah. Okay. Good question though. Yeah. So now look at this. Let's say that like I denote like the ith column to be AI, and like so this thing actually is something like sum over all I from I to U, AI times CI. Right? This is just how you multiply the matrix to a vector. Like yeah, just there. Okay. Maybe I write J. Yeah. Okay. And so what I'm gonna do is that I'm gonna like move. I just write AI CI equals this minus all the J that is not I, AJ, CJ. And CI is 1, so I can remove CI. Okay. So what is this now? It's the probability that AI, which is one column of A, agree with this vector. And this vector is independent from AI. Right? This vector, like all this thing, it depends on all other entry of A, which is not at the column I. With me? Okay. So now it's just basically asks like what is the probability that this column AI, which is just a random vector, right? Because agree with this thing. So this is just a random vector of dimension m, and it must agree completely with this. Each of the bit agree with probability 1/2. So this is again 1/2 to the m. Okay. Okay. So now I have said that we have seen that. Actually, I want to show. Like, we have analyzed two events, right? The first event here, and the second event here. Okay. Actually, I should say that if these two events happen, then this thing happen. Like this is if and only if actually, because like if this and this is true, it implies this thing. And if these two things is true, it's just from the definition that this is the case. Yeah.
Sorry, on the last step of what we did down there, where you crossed out like zi and
Yeah.
how can we say, so I get why the other columns of A are independent of AI, but how can you say that for A1 or alpha 1 and alpha 2? Because aren't they computed using A? So I would think that they wouldn't be.
Alpha 1 and alpha 2 is like a some fixed vector. We ask for the event that given x1, x2, alpha 1, alpha 2. Right now you think of x1, x2, alpha 1, alpha 2 as some fixed vector. And now the only thing that is random is just A and B. This is like a probability over A, B. That's the only thing random right now. Okay. Okay. Make sense? Okay. So we see that this event happened with this probability, this event happened with this probability, and they are actually independent from each other because like a B is independent from everything here. So the probability that these two events happen is just at the same time, it's just this probability times this probability. So it means that we get what we want. Okay. I put the calculation here, but you like I need to move on for now. Okay, so at least you see that we can construct an efficient twice independent family, so that the space that it needs to represent a function is just like something like polylog of the range and domain. Also, the time to evaluate is polylog too, but we don't care about time right now. But it's just an efficient one, basically. Okay. So now, okay, what we want to do is to remove the idea of random function with the twice independent one. So what we need to do, we need to look at the analysis that we have done and see like what property from the random function did we use, and see if we can replace it with a simpler family that is efficient, right? So what we did in our analysis is two steps. One is to compute the expectation, and one is to compute the variance. Let's look at the first step. When we compute the expectation, here what we need from our hash, like from the property that we need from our hash family is that H is uniform. Everything mapped to 1 with probably like a 1 over the range. So it's uniform. But this would be true if our family is sampled from twice independent family. Right? Twice independence is like implies uniformity. Why? You can check this, but like note that universal family is not enough. So at least here, 2 y's would be enough. Okay. So that's the part in the when we compute expectation. What about when we try to compute the variance? This is a step that we need that xi's are independent. Xi, note that xi is just like the event that the ith element mapped to 1, right? So it means that we want this event to, like the event that it mapped ei to 1 to be independent from each other. Okay. So this looks quite problematic because it seems like we want all the xi to be independent from each other. like it seems like we need DE wise independent, but not really actually. The reason is that for this step to be equal to this step, we need something much weaker. Like here is like we need that the variance is linear. But actually variance is linear already when you have two wise independents. Okay. So even when all the xi are two wise independent, you already have that linear, like variance is linear. Okay. And the calculation is straightforward. I will not show, like I will skip it. You can look at it, but I just expand the sum, rearrange the term, and at the end of the day, there's gonna be like this place where this place can cancel out because I just need that each pair of xi and xj are independent from each other. It's just about pairwise relationship that need to be independent. So once xi and xj for each pair are independent, this thing cancel. And once this thing cancel, you just get that this is the sum of the variance for each for like sum of variance of xi. Okay. So you can check that, but anyway, it means that this part, this step, I just actually need that xi are two wise independent, which means that what we need is that the event that the hash function map element I to 1 are two wise independent. And this would be true if we sample our hash function from two wise independent family. Okay. So this is all the property that we need from our hash family. And we see that all the step is enough to use two wise independent family. So it's like we can just now replace the random function with a function that is sampled from two wise independent family. And we see that we have seen that like the space of H is like a log square, like log of the range times log of the domain times log of the range. Both of these are at most u, so it's like log square u at most. So now we are good. Okay. And you actually can improve this to log u. It might be in the next homework. Okay. Any question up to now? Okay.
Can't we easily improve because we're using probability 90%, but since we set t somewhat arbitrarily as like 40 over epsilon squared, couldn't we just, since we already have it as O of epsilon squared, couldn't we do it with arbitrarily high probability?
Exactly. Very good point. So this is the next thing that I'm gonna do. Try to improve this probability to be something as high as we want. And you're right that what we can do is just to set t to be higher, and that would boost the probability. There is a better way. Okay, so let's try to boost the probability. Okay, so right now we fail with probability like 10%, but like what would be it would be much more convenient is if we like fail with probability like a delta with tiny delta. Like delta is smaller than like 1 over nu to the c for any constant c. So what I mean, I want it to be success with high probability, where high probability is like the notion that I mentioned last class. Okay. And the first attempt that Scott just mentioned, we can just, if we want failure probability to be delta, we can just increase t, right, to be this big. And we can see that like the probability that we answer wrong is just at most delta, because we have seen this before. This is the probability that we are wrong. if t is this big, then this failure probability is at most delta. Okay, we can just set t to be big. But the problem is that the space is linear in t. So if t is really big, then this is just too big. Okay, because I think of delta as like something really tiny. Okay. So there is like actually a better way and more black box solution, and the solution is here. And this is like a really generic way to do this. So like it's really useful. The idea is just to take majority. So the solution is just make independent copies of your algorithm that is correct with 90%, and just output the majority of the answer. Really natural, and it works. Why is that?
New launch.
Okay, so I'm just gonna use yi to indicate that the ith copy answer is correct. And let's say that y is the sum of all the yi. So in expectation of y is just 90% of all the copy, because each of them is correct with 90% at least. Maybe I should use at least. Yeah. Okay. Each of the yi is correct with 90%. So in expectation, y is at least 90% times c. Okay. But if we are wrong, if the majority is wrong, it means that y is actually less than 0.5 c. Right? It means that more than half of the copy is wrong. So like the correct one is less than half of all the copies. So I expect y to be huge, to be like a 0.9 c, and I'm wrong if y is less than 0.5 c. So it deviates from my expectation by like some constant factor. So this is what will happen. If the majority is wrong, then y is less than the expectation by like a 0.4 c. What do you think? What tools should we use to bound this probability that y deviate from expectation by something? What is a good tool right now? I want to say that this is tiny.
Chernoff?
Yeah, Chernoff. Why?
Because we're doing a sum over independent indicators.
Exactly. When it's sum of independent indicator, and you want to bound like you want to make it concentrate, just use Chernoff. It's just strongest, and we can use Chernoff. Like whenever you can use Chernoff, use it. And right now we can use it. And if you use Chernoff, you're gonna get like basically something like exponential in C. Like you can verify this, but I set C to be log of 1 over delta. If C is log of 1 over delta, this is going to be 1 at most delta. Okay. So now I'm done. Okay. And this just works for any problem. And now you see that the first attempt solution increased the space by 1 over delta. This solution increased the space in total by log of 1 over delta. So it's like exponentially better. Okay. Good. Let me finish this with another one. Like we want to work with, like we want to remove the threshold. We solve the threshold version, and we also want to be correct at all time. Like we can like right now like improve our algorithm easily. Like my point here is like once you have that the correctness holds with high probability, it's quite easy. You will see that you can strengthen your algorithm like to do whatever, okay, in quite flexible way. Okay, so let's try to get approximation, not just solve the threshold version. Okay, so what I'm going to do is just run the algorithm for each threshold, for the algorithm that have the threshold for many threshold. When the threshold is 1 plus epsilon, 1 plus epsilon square, cube, and so on, up to u. Just do it for every many threshold, where each threshold is like the gap between each threshold is like 1 plus epsilon factor. Okay. And then just find the largest threshold such that the algorithm still says yes and return that. Really natural, right? And okay, suppose that every copy for each threshold is correct, then what you return would be like 1 plus epsilon approximation, because each of the threshold is like just 1 plus epsilon gap from each other. So you would return the correct answer. And how many copies are there here? It's just log of u base 1 over 1 plus epsilon. So that's just log u over epsilon. So it increased the space by this factor, which is still pretty long. Okay. And you actually can show easily that all copies will be correct with good probability. Why? Just use turn off union bound right now. There are like this many copies. The probability that there exists a wrong copy is just log the number of copies times delta. But delta right now is tiny. Delta is just like really tiny. So it's just 1 over some big polynomial of nu. Make sense? Okay. So this approach would work for any problem. And okay, I should finish. Like if you want it to be correct with at all time step, like each time step is correct with like really high probability, like the failure probability is tiny. And you can just now use union bound to say that like the time step that is wrong, just use union bound, and like there are n many time steps. So the probability that there exists a wrong time step is tiny again. Right? Okay. So that's how you're done. Like, so you say like all this trick you can do it very quickly just by union bound once you have high probability guarantee, and it increases your space by like polylog factors. So here we are done. Okay. So that would be it for today. Let me wrap up. Like this is gonna be on the next time, maybe the majority one. But what have we learned today? 1 sec. Okay. We learned the model of streaming algorithm. We see distinct element and the concept of two-wise independent hash family. And this generic technique is really important. I want you to take note of this, because it's just you can use it all the time to boost probability by taking majority. And once you want to solve approximation problem, just solve the threshold version first, and then you can solve the original one easily by like doing this for each threshold. Okay, so that's it for today. Yeah, see you next class.